Hi everybody, thanks for being here. I'm Babineau and I'm currently doing a master's degree in physical oceanography under the supervision of Dr. Ruth Musgrave. Today I'm going to talk about turbulence in the deep ocean and understanding the interaction of currents with underwater topography. In this talk I will start by introducing Lee waves, what they are and why they're interesting, which will lead to my research project and a model that I am using, MIT GCM. I will briefly present its setup, its background. Also, I will present my numerical setup and the simplifications that we make, and finally, the preliminary results that I have. First, what is a Lee wave? They are oceanic or atmospheric internal waves created when a current flows over topography and encounters an obstacle like a mountain. The flow is going up on the windward side and down on the lee side. Then it's going to bounce back up and stabilize itself at a new height. This is what the picture to the left is showing. To the right, we can see an example of an atmospheric Lee wave. They are often observed around islands since the ocean surface is relatively flat compared to the height of the island. They are easier to observe than oceanic Lee waves because when the flow bounces back up, we can see that over here, there is a stripe of clouds that appear on the crest. Now, let's talk about the physics of the Lee wave. They propagate upward and away from the generation site. Their group velocity, CG, is oriented with the slope of the wave. It represents the rate at which energy is transferred. The phase velocity, CP, is making a 90-degree angle with the group velocity. These two arrows are in a frame of reference that is moving with the flow. If we want to get a group velocity in a frame of reference that is fixed with topography, we can call that CG topo. We need to add the velocity component U to the group velocity CG. This arrow is pointing upward, clearly showing the direction in which the wave is propagating. As the Lee wave is propagating upward in the flow, it can steepen and break like a beach wave. The animation here to the right is showing how a beach wave is steepening and breaking and how this is leading to turbulence. So we can see this over here. The wave is getting steeper and then it's breaking. Even if Lee waves are breaking in a way that is similar to beach wave, they are quite different. First, they are stationary wave, meaning that they do not propagate in the horizontal direction. And secondly, they steepen because of the nonlinearities in the flow, not because they are going over shallower and shallower water. So why are oceanic Lee waves important? Well, they transfer energy away from the generation site. As I said before, they can steepen and break, which is going to lead to turbulence. The turbulence is dissipating kinetic energy and it contributes to ocean mixing, which is key in physical oceanography and biological oceanography as well as chemical oceanography. Another aspect of the wave that is important to consider is that there are discrepancies between observation of energy flux and what the theory predicts, which means that we do not fully understand Lee waves, this phenomenon. Having a better theoretical understanding would help us to have a better idea of the energy dissipation and help us to include this phenomenon in the global models. Historically, theoretical studies have been based on depth uniform currents. However, the picture here down to the left is showing something different. These are velocity profiles taken in Drake's Passage in between Chile and Antarctica. As we can see, the velocities are not necessarily uniform in depth. Furthermore, these are realistic velocity profiles because Lee waves have been observed at this location. So this leads us to the hypothesis that assuming depth uniform currents is incorrect, and this may lead to the discrepancies that we observe between theory and observation. To test this, I will run numerical simulations with differing currents and quantify the energy flux. Then I will compare these results to observation to see if a more complicated velocity profile leads to a better prediction. Now, let's take a look at the governing equations. First, one important thing to remember is that the flow is going up over the bump and down on the other side. This means that the shape of the topography dictates the wavelength of the Lee wave. The wavelength is L. Also, the horizontal wave number K depends on L, and we can see this relationship in equation number 1 that is written just over here. Another important parameter is the buoyancy frequency N, which is a measurement of the stability of the fluid to vertical displacement. We have that vertical stability because the fluid is stratified. We can see the stratification with the temperature profile right over here. And this also means that we have a vertical density gradient. So the buoyancy frequency depends on the density gradient, and we can get that gradient by taking the derivative over z of a simplified equation of state. So these equations lead us to the dispersion relation that is written just over here. It describes the spatial structure of the wave. From this equation, we can get some important information like the slope of the phase line. This is given by the ratio of k over m. And with this slope, we can get also the angle over here. Just a quick word about this equation over here. M represents the vertical wave number, k the horizontal wave number that we have seen in previous slides, that it is dependent on the length scale of the mountain or the topography. Then N is the buoyancy frequency and U is the velocity in the x direction. It is important to understand that this is the velocity of the current, so from far away from the mountain, not the velocity directly at the Lee wave. And then F is the Coriolis parameter. Let's talk about MIT GCM, which is the model that I am using for my simulations. It is using a C grid on the horizontal space. This means that the velocity in the x direction u and the velocity in the y direction v are not computed on the same grid point. For the vertical axis, it is using a z-level model. It is using straight lines to discretize the water column. This type of model has a little bit more trouble to solve the flow at the boundary or at the topography. However, MIT GCM implemented an algorithm at the boundary to overcome this difficulty. The model is also using finite difference approach, and we can run it in a hydrostatic or non-hydrostatic way. So for my experimental setup, I'm doing some preliminary work right now, so I have a highly simplified model, which means that my bathymetry is only a little bump, like this one. We can see that the resolution in the x direction here is higher close to the bump, which is useful because that's where the interesting stuff is happening. Further away from that specific place, we are less interested in the phenomenons, so we can have bigger delta x, so a lower resolution. This is going to lower the computational cost and get the stimulation faster. Also, we have this temperature profile, which might seem at first glance a little bit unrealistic, but since the Lee waves are happening in the deep ocean and the deep ocean is not very much stratified, this is a good approximation. Simplification that is worth mentioning is that we have higher viscosity. So this is the graph from the same simulation but ran with different viscosity. And we can see that even if it's higher and even if it's not the same as you would see in the ocean, we can get rid of some small-scale phenomena that the model is trying to resolve. And we are not really interested in these ones. So it is making the solution smoother without affecting really the Lee wave. So one last experimental parameter to set up is the current. Here we can see that the current is constant in time. It is also constant in depth. This is one simplification to make sure that the model and the hypothesis that we made fit with the theory. Also, we can see that we are gradually accelerating the flow, which is helping us to get rid of any undesirable physics that would happen if we had that sudden burst of velocity. Last thing that I want to point out is this little animation here, we can see as the time and the flow develops that the Lee wave is propagating upward as those little stripes are going up. So we can see that the model is producing the result that we are expecting. The animation on the previous slides showed that the model is producing a sensible output. To verify how accurate the results are, we can compare the wave angle to the theory. So for the theoretical angle, we are using the dispersion relation that I presented a couple of slides ago, and we have this ratio of K over M, and it is giving us an angle of 65 degrees. For the experimental angle, we have 63 degrees. It is quite nice to see that these two angles are close to one another. However, I had to draw this line on the graph, so the experimental angle is quite an approximation. But the fact that they are similar is telling us that overall our simplifications are okay and that the model is giving a good result. One takeaway from my presentation is that Lee wave propagates away from the generation site. They can steepen and break, which leads to turbulence in the ocean's interior. This in turn is contributing to ocean mixing. Also, my preliminary work showed that the theory and the model agrees. And finally, for the next steps, I would like to run some more realistic simulations. First, I will use currents that are very in-depth. Secondly, use a more realistic bathymetry. As I've said, Lee waves have been observed in Drake's Passage, so I might use bathymetry from there in order to compare the results from the model to some observations. Finally, a better parametrization of viscosity will improve the accuracy of the model. So I would like to thank you all for listening to me. Also, thank you to Ruth, who's my supervisor, and I wish you all a great day.